Section 3.6, Rational Functions. Okay, so let's start by just defining a rational function. So this is a function, y equals f of x, which is in the form f of x equals p of x over q of x. And this is where p and q are both polynomial functions. Okay, so simply put, a rational function is a polynomial divided by a polynomial. So the domain of a rational function is just the set of all real numbers except for those which make the denominator equal to 0. Okay, and this should kind of make sense. I mean, first of all, because polynomials on their own, they have a domain of all real numbers. That's kind of a special thing about polynomials. Every polynomial's domain is all real numbers. So if we do a polynomial over a polynomial, we're only creating risk in the denominator, so zeros of the denominator are not in the domain. So some examples, there's quite a bit of diversity, as far as how these things can look. The first example, I'm going to call this p of x, just 1 over x. Okay, so this is the most simple rational function. The numerator 1, I know that doesn't look like much of a polynomial, but technically it is. It's just a polynomial with only a constant term. And then x, in the denominator, is a very, very simple polynomial, degree 1. And we oftentimes consider this the parent rational function. So we can talk about like transformations and translations, reflections, all that stuff in terms of this parent function. And the domain of this, in this problem, the denominator polynomial, which we usually call q of x, is just equal to x. Okay, so the only 0 of q of x is 0 itself. So the domain would be equal to, just all real numbers except 0. Another example, we'll call this f of x, could be something like this. Okay, so another rational function. The numerator and denominator here are both linear, okay? And the domain of this one, we could get by, generally we set the denominator equal to 0 and solve. And if you did that here, you would get that the only 0 of the denominator is 2/3. So the domain for this one would be, negative infinity to 2/3 union with 2/3 to positive infinity. Okay, so all real numbers except for 2/3. And then, one more example. For this one, we're going to have 2x plus 4 over x squared minus 3x minus 10. Okay, so for this one, we've got a, degree 1, a linear function divided by a quadratic. Okay, so the degree of the numerator and denominator don't have to be the same. And for this one, just since we're thinking about domain, looking at the denominator, notice that this denominator, if we set it equal to 0, we could solve it by factoring. This factors to x minus 5 times x plus 2. And we get these two zeros, x equals 5, x equals negative 2. So the domain of this rational function is going to be negative infinity up to negative 2, union with negative 2 to positive 5, union positive 5 to positive infinity. Okay, so there's just a few examples and their domains. So I find this section to be super rewarding because we're going to get into graphing these things, and they have really interesting graphs. And once you get the hang of, just what to look for in a rational function, they tend to be kind of manageable, I guess, to graph as well. You can get a surprising amount of information by just kind of looking at the function. But just like with, when we're graphing any function, we're going to be paying close attention to intercepts, symmetry, transformations, that kind of thing. And then a couple of new things that we need to consider is, and this is going to relate to asymptotes, we have to consider the domain of f and the degrees of the numerator and denominator functions. Okay, so before we get into asymptotes, so asymptotes, this is going to be kind of like the big takeaway from section 3.6. Let's just look at a real basic example here. So we want to graph f of x equals 1 over x minus 2 and see what happens as x, absolute value of x, gets large, and what happens when x is close to 2. All right. Well, for this function, there's a couple different ways we could do this. We could do a table of values, but another way we could do it is we could look at the parent function p of x, which is equal to 1 over x. Okay, so that's the parent function. So notice that f of x, and I'm thinking along the lines of like what we saw in section 2.2, if you want to look back to that section. We've got the parent function, and f of x, the function we're actually looking at, this is just equal to p of x minus 2, right? Basically switch the x for an x minus 2 in the parent function. So the transformation here, the transformation from the parent function to get to the graph of f is we just shift the parent function graph 2 units to the right. So this is a horizontal shift to the right by 2. Okay, so we can get this from the parent function. So quickly, I want to give you what the parent function looks like. So the parent function p of x, and you might remember this one, and I'm going to make a little table of values off to the side here. So x, and then the parent function p of x. So it's pretty easy to evaluate, if I want to plug in like -2, -1, 0, 1, 2, just to start there. I get -1/2, I get -1. Putting in 0, we have a problem, right? We get 1 over 0, so 0 in the denominator, so it's undefined at 0. And we kind of knew that because we were just looking at the domain of this very function right here. 0 doesn't work because it's 0 the denominator. Okay, and then plugging in 1, we get +1. Putting in 2, we get +1/2. So, so far, all that we have of the parent function is, here, let me mark out my axes here. We've got these ordered pairs. But that's not quite enough. I might plug in some larger values, like if I plug in -10 and +10, I get negative 1/10 and positive 1/10. So it's kind of like apparent that as x gets larger and larger, like if I plug in 10, I get 1/10. So I can see that the graph is getting like closer and closer to the x-axis. In fact, if I plugged in like, 1,000 for x, I would get 1/1000th, which is a tiny, tiny number. So in the long run, this graph is going to approach the x-axis. And that's as x goes to positive infinity and as x goes to negative infinity. So on the left and on the right. And then, okay, what about as x gets really, really close to 0, right? So still working on my table of values here on the left. What if I plugged in some really small number that's really close to 0? How about like, from the right, like what if I put in 1/1000? Well, 1/1000, just multiply by the reciprocal, and we get 1000. Okay? So it turns out that as our x values get really, really, really small, so like as our x values are approaching 0, the outputs of the function get really, really, really big. Okay, and same thing happens on the left, but in the negative direction. So it's a very imperfect picture. Your calculator could do a better job of getting a good looking graph, but I hope that you get the idea here. Okay, so notice that the graph is getting really, really close to the x-axis, or the line y equals 0. And it's also getting really, really close to this vertical line, x equals 0. So y equals 0 is what we call a horizontal asymptote. And x equals 0 is what we call a vertical asymptote. Okay, and all of this kind of like this is some pretty interesting behavior, and this all stems from this fact that like if we have 1 divided by a really big number, this gives us a really small number, right? And similarly, if we have 1 divided by a really small number, like 1 divided by 1,000th, we just get 1,000, so we get a big number. Okay, so this is kind of the principle that determines this really interesting behavior of rational functions. Okay, well anyway, now that we have a good idea of what the parent function looks like, to get the graph of f of x, we're just going to shift it 2 units to the right. Okay, so here we go. Now we're actually going to graph the function. So I'm going to shift my parent function 2 units to the right, and this isn't going to change kind of the main features of the graph. I'm still going to have a vertical asymptote and a horizontal asymptote. Everything is just going to be shifted to the right by 2 units. So now my horizontal asymptote is going to be at the line x equals 2. And my horizontal asymptote isn't going to change. It's still going to be at the line y equals 0. So I'm just shifting each of my ordered pairs off to the right by a couple units. And here is what my graph looks like. Great, so there's the graph of f. And that vertical asymptote at x equals 2, makes sense when we think about the graph. I mean, because f of x is equal to 1 over x minus 2. And, the domain of this, since the denominator can't be 0, is going to be from negative infinity up to positive 2, union with positive 2 to positive infinity, because we have to jump over x equals 2 because we can't plug it into the denominator without getting a 0. So I agree with that asymptote there at x equals 2. We cannot have that as an input. Okay, well, consider that your kind of quick introduction to very basic rational functions. So now let's talk about asymptotes in a little bit more detail. So some notation here. So remember when we were talking about end behavior, and we would use this notation, like as x goes off to positive infinity, then f of x goes to positive infinity. And then as x goes to negative infinity, f of x goes to negative infinity. Like we would use that kind of notation to say, hey, the end behavior of this polynomial function goes like, this and this. So we've kind of already seen this type of arrow notation in the context of end behavior. So now we're going to use the same kind of notation to deal with asymptotes. So asymptotes, let's say that we have a 0 in the denominator at a, where a is some real number. So, looking at this last function that we were just working with, notice that as x approached 2 from the left-hand side, we saw that, f of x was going to negative infinity, right? So that describes this part of the graph. And then as x was approaching 2 from the right-hand side, f of x was shooting off to positive infinity, right? So there's this branch going up like that. So I was kind of speaking through that as I was writing it. This notation, 2 with the little minus sign up there and then 2 with the little plus sign up there, that communicates which direction we're approaching that x value from, right? Because if we're approaching this asymptote from the left or from the right, we could have different types of behavior depending on which side we're approaching from. Okay, so that's what we're talking about here. As x approaches a from the left, so the minus sign means we're approaching from the left. And this is x approaches a from the right. And then if we just have x approaching a with no plus or minus sign, that means from both sides, from the left and the right. Okay, and every so often we'll have an asymptote that looks something like that, and maybe the behavior of the function looks like this, where, hey, maybe it's approaching positive infinity from the left and from the right. Okay, so if the limit from the left and the right of a are both going to positive infinity or both going to negative infinity, then we can just use this notation, which communicates that the left and the right side have the same behavior. Okay, and then x approaching infinity, this basically deals with end behavior, right? Just like we were talking about with polynomials. So as x goes to negative infinity, that means x becomes unbounded in the negative direction. So as x goes to negative 1,000, negative 10,000, negative 100,000, moving off to the left without ever stopping. And then as x goes to positive infinity, that means that x becomes unbounded in the positive direction. Okay, so vertical asymptotes. So the line x equals a is a vertical asymptote of the graph of f if any of these conditions hold. And then here they are, there's 6 of them. So as so if f of x goes to negative infinity as x approaches a from the left, or if x approaches negative infinity as x approaches a from the right, and basically if we see the output values going to positive or negative infinity from the left or to the right of some particular x value, or both, right, then that means that we have an asymptote. So pretty much if you ever see like unbounded behavior of a function at some x value, then that means that we're going to have a vertical asymptote there. Okay, and then if the y values are approaching, positive or negative infinity near x equals a, then it will have an asymptote. Okay, that's kind of a simpler way of putting it. Okay, and a rational function with a vertical asymptote is discontinuous at x equals a, and we call this an infinite break. The graph will never cross a vertical asymptote. Okay, so to kind of tie in continuity here, remember continuity is like if we can draw the curve without picking up our pen, right? So if I think of the graph of like a polynomial, polynomials are famously, continuous for all real numbers because there's no holes in the graph, there's no asymptotes or anything like that. But obviously, if I have a vertical asymptote, I'm going to have to pick up my pen when I'm drawing my curve. And if I'm forced to pick up my pen, that's what we call a discontinuity. Okay, so vertical asymptotes cause discontinuities. All right, and now let's talk about horizontal asymptotes a little bit. So the line y equals c is a horizontal asymptote if the graph of f, if it meets any of these conditions. So f of x approaches c as x goes to negative infinity, or f of x approaches c as x goes to positive infinity. Okay, so again, I'm going to look back to this problem we just did. So when we were looking at the parent function here, remember we plugged in some big numbers. Like if you plug in 1,000, for example, you get 1 over 1,000. If I put in, 10,000, I would get 1 over 10,000. So this whole thing where I'm like, letting x go to 1,000 and then 10,000, and then I could go to 100,000. So plugging in larger and larger values of x, I'm writing right here, that's kind of like letting x go off to infinity. Okay, and we observe what happens. And what happened in this case is we got, 1 over 1,000, 1 over 10,000, and so on. And what we see is that these values are getting really, really close to 0. Okay, so that's why we ended up with a horizontal asymptote of y equals 0. Okay, so this is technically end behavior, right? It's like as we go way off to the right, what happens? As we go way off to the left, what happens? But when we talk about end behavior, we're used to hearing it with polynomials, where it's like it always shoots off to positive infinity or negative infinity. So this is a different type of end behavior where it doesn't go off to positive or negative infinity. It might just approach some, some horizontal line. Okay, so yeah, I really do think of horizontal asymptotes as end behavior, where it just doesn't shoot all the way up or all the way down. It just, converges to some real number. And, okay, rational functions will have at most one horizontal asymptote. So we don't have to worry about there being too many of these. There's only one. Slant asymptotes. So the line y equals mx plus b is a slant asymptote of the graph of f of x if any of these conditions hold. If f of x approaches mx plus b as x goes to negative infinity, or f of x approaches mx plus b as x goes to positive infinity. Okay, so if a graph has a slant asymptote, then the graph cannot have a horizontal asymptote. So sometimes, let's say we've got some rational function and, maybe it's got a vertical asymptote right here. So sometimes it doesn't necessarily have a horizontal asymptote. Sometimes it'll have a slant asymptote. So the dotted line is going to be in the form y equals mx plus b, where m doesn't necessarily equal 0. And we can get these really cool graphs that look like this. Sorry, I can do a little better than that. So we can get these kinds of graphs where, notice that the behavior near the vertical asymptote is pretty normal. It's just like going down to negative infinity to the left, up to positive infinity on the right. But these, the slant asymptote causes, rather than, having the function converge to some horizontal line and just flatten out, it kind of shoots upward, but it follows, it kind of uses the slant asymptote as sort of like a guardrail that leads it towards positive infinity on one side and negative infinity on the other side. So, we're going to see examples of all these things that I'm talking about, so don't let yourself feel too overwhelmed right now, but this is just another situation that we might run into. And I'm going to teach you, what to watch out for and how to tell if we're going to have a slant asymptote rather than just a normal horizontal asymptote. Okay, let's talk about how to find these asymptotes. So let's start with vertical asymptotes. So suppose, P of x and Q of x have no common factors, so that means that this rational expression can't be simplified. So if Q of a equals 0, so a is a 0 of the denominator, then the line x equals a is a vertical asymptote. So if we want to find vertical asymptotes of a rational function, like we're asked to do in example 2, we just have to find the zeros of the denominator. So I'm going to set, Q of x equal to 0. So that's going to be x squared minus 9. And, this factors to x plus 3 times x minus 3, difference 2 squares, right? So I get these two zeros, x equals, positive 3, and x equals negative 3. So these are actually, the equations of the lines of the vertical asymptotes. So I'm just going to box those up. All right, so what this means is, I'm not going to go through the trouble of graphing this whole thing. But, when I do go to graph this, I'm going to have these, vertical lines here at negative 3, x equals negative 3, and x equals positive 3. And I'm going to have some behavior here. I think that for this particular function, I think we have behavior that might look, kind of like this. Or no, I think that one goes up like that. Okay, so this type of picture, although it's, not at all accurate, this is a really common type of picture. We'll have more than one asymptote, and yeah, behavior like that is not uncommon. But anyway, for this one, really, we just wanted to figure out where are those two vertical lines. So there they are. And for example 3, we want to do the same thing. For this one, we want to find the vertical asymptotes of x plus 1 over x squared plus 4. So I will set Q of x equal to 0. So Q of x in this case is x squared plus 4. So this polynomial on the left, this quadratic, does not factor over the real numbers. I could solve it by taking square roots. So subtract 4 from both sides and take the square root, and I get x equals positive 4, when I take the square root, positive 2i, and x equals negative 2i. But 2i and negative 2i are not on the x-axis, right? So these aren't actually going to represent vertical asymptotes. So interestingly, for this problem, there are no vertical asymptotes. So I'll put a box around that. Okay, so, zeros of the denominator tend to correspond to vertical asymptotes unless there is an exception to this, unless that zero of the denominator is also the zero of a zero of the numerator. Okay, so this is kind of like, if there are common factors between our numerator and denominator. Okay, so let's talk about that situation. So what if p of x and q of x have common factors? So assume x minus a is a common factor. So then p of x over q of x might look something like this, like we can factor out x minus a from both. Okay, and the temptation here is to cancel out those common factors, and then it's as if they never existed. However, it turns out that even though those factors cancel out, we still are not allowed to plug a into this function, right? So even though they cancel out, a is still not in the domain. Okay, and this creates what we call a hole in the graph. So let's look at a little example here. So f of x equals x squared minus 1 over x minus 1. So, without paying attention, really, you might look at this and think, oh, we have a vertical asymptote at x equals 1 because, x equals 1 is the zero of the denominator. But, if you're on top of things, you'll notice, oh, well, that numerator factors to x plus 1 times x minus 1. And this is over x minus 1. So we have a common factor of, x minus 1. But, even though we can sort of cancel this out, and this is like sort of, I'll do like maybe a little squiggly thing, like this kind of simplifies to x plus 1. But it turns out that that's not actually what f of x is. Okay, because even though those factors cancel out, this is how we defined f of x initially. So, x equals 1 is not in the domain. Okay, so x equals 1 is not in the domain even though the factor x minus 1 is common to the numerator p of x and the denominator q of x. Okay? So the way that we can think of this now is it's kind of like for any number other than x equals 1, if you plug it into f of x, you're going to get the same output as x plus 1. Okay, so another way of writing f of x, so f of x, it's originally defined as x squared minus 1 over x minus 1. So another way to write this is like, this is just equal to x plus 1, so the simplified version if we cancel out that common factor, as long as x does not equal 1, okay? and then it is undefined if x is equal to 1. Okay. So it's sort of like, we can cancel out that common factor, but we're not allowed to forget that x equals 1 is not in the domain of the function. So the graph of this is going to be pretty cool. The graph ends up just being like, the graph of that line, y equals x plus 1, which is just a linear function. It has slope 1, it has y-intercept 1. So f of x is going to basically have the same graph as that linear function. So it's going to look like this. Except at x equals 1, there's going to be a hole. There's going to be like an open bubble. But aside from that, it's going to look just like the graph of y equals x plus 1. So there is f. So I'll just make a little note here. Graphically, f looks like y equals x plus 1, except it has a hole at x equals 1. All right. So that kind of gives you your technique for dealing with common factors between the numerator and denominator of a polynomial function. If you're being asked to graph, you are essentially just graphing the function that results from canceling out the common factors, but you have to include holes for any values of x that would have caused a 0 in the denominator in the original expression of the function. Great. So now that's it for vertical asymptotes for now. Let's talk about horizontal asymptotes. So here's just like a kind of general way of expressing a rational function, right? So we've expressed polynomial functions in this way in the past. So this is just kind of like, a polynomial function over a polynomial function, just expressed sort of generally. So notice that the numerator has degree n. So I'll say, the degree of p is equal to n, and the degree of q is equal to m. All right, so notice that these are not the same degree. And we're not specifying if, they're equal or if one, which one is bigger than the other, any of that. We're going to come up with some general rules for each of the cases that arise. So thinking about end behavior. End behavior for a polynomial is determined by the leading coefficient and the degree, right? So remember, if we have like an odd degree polynomial with a negative leading coefficient, then the end behavior is going to be up on the left, down on the right. So we kind of like discovered why that fact is a fact back in whenever that was, section 3.1 maybe. And the way that we did it is we did this little proof which involved pulling out the factor x to the n. So we're going to do something kind of similar in this problem. Okay. So, okay, f of x is equal to, p over q, and then here it is like all expanded out. So what I'm going to do is I'm going to factor out x to the m. So that's like the highest degree in the denominator from the numerator and the denominator. So that's what I'm doing in this step right here. So let's see what this looks like. So in the denominator, I'll factor out x to the m. And remember, on the inside of the parentheses now, I'm going to divide each of these terms by x to the m. So I'll just be left with b sub m, that's like the leading coefficient, plus b sub m minus 1 divided by x, right? Because x to the m minus 1 divided by x to the m, I would just have one factor of x in the denominator, plus, dot, 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 until we get down to b sub 1. This is going to be divided by x to the m minus 1. And then plus the constant term b sub 0. This is going to be over x to the m. So that's what it looks like when we factor out x to the m from the denominator. So now in the numerator, if I factor out x to the m, so I'm going to be left with a sub n times x to the n divided by x to the m, plus, a sub n minus 1 times x to the n minus 1 over x to the m. Oh, sorry, that should have been a plus sign right there. And then plus, dot, 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 all the way down to the end until we get a sub 0 divided by x to the m. Okay, so then, the x to the m and the x to the m can cancel out. And here's what I'm left with. So I'm going to write this kind of big here. So in the numerator, I'm going to write this as, a sub n, the leading coefficient, and then x to the n over x to the m, plus a sub n minus 1 times x to the n minus 1 over x to the m, plus dot, 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 all the way down to the end. Here I should have had these look like exponents in here. Okay, and then in the denominator all I'm left with is b sub m plus b sub m minus 1 over x plus, okay, all this stuff. All right, so now that I have this, I know that this is a mess and you're probably wondering what the hell we're doing. But this is another way of expressing f of x. And looking at this notation, so remember, end behavior is all about what happens as x goes off to positive infinity or negative infinity, right? So down here I'm going to say, so as x goes off to positive infinity, well, let's think about, what's going to happen to f of x. Well, looking at the denominator, all of these terms are going to go to 0 over here, right? Like, okay, this, like a constant divided by x. As x goes off to positive infinity, that's just going to go off to 0, right? Because the denominator is going to get really big and, they're all going to cancel out, okay? So these are all going to go to 0. So that term is going to go to 0, that term is going to go to 0, that's going to go to 0, that's going to stay. Okay, so the denominator, it's kind of clear what's gonna happen. So I'll say as x goes to positive infinity, f of x is gonna go to, so the denominator is just gonna go to b sub m. Okay, so now the numerator is not so clear because, all right, it's gonna depend on how the degrees of p and q match up to one another. Because this little expression right here, x to the n divided by x to the m. So if m is larger than n, then this is going to simplify. this is going to simplify basically to, 1 over x to the m minus n. Okay, so if m is bigger than n, then this whole thing is going to go to 0, right? But if the degree of the denominator is smaller than the degree of the numerator, then this is going to go off to infinity. All right, so it kind of depends, like, the degree of the numerator versus the degree of the denominator. Okay, and there are 3 cases that come up. Okay, so if the degree in the numerator and denominator are the same, the numerator is bigger and the denominator is bigger. So as far as what happens to the numerator here, there are 3 cases. So that's what we're going to look at in this next box here. So if the degree of the numerator and the denominator are the same, then, okay, looking back up to the picture here, then this is going to cancel out and this is going to become 1 up here. This is going to become 1, and all of those other terms are going to go to 0. So case 1, if the degrees are the same, up top we're just going to be left with a sub n. Okay, so case 1, the degrees are the same, and then we have a horizontal asymptote y equals a sub n over b sub n. Okay, so this right here, to sort of put this in simple language, this is the ratio of the leading coefficients. All right. Okay, what if the degree of the numerator is less than the degree of the denominator? Well then, remember we're paying attention to this right here. So if the degree of the denominator is bigger, then as x goes to infinity, this thing is just going to go to 0. All right? So then, rather than having a sub n up here, we're going to get 0 in the numerator. So that's why, if the degree of the numerator is less than the degree of the denominator, y equals 0 is the horizontal asymptote. Okay, and we've already seen an example of this. If we look back up to this first page of the section, this problem right here, f of x, notice that the degree of the numerator is equal to 0, right? Because it's just a constant term. And the degree of the denominator is equal to 1. Okay, so the degree of the denominator is greater than the degree of the numerator, and that's why we got this horizontal asymptote of y equals 0. Okay, so this is an example. If the degree of the numerator is less than that of the denominator, we are just going to have an asymptote at 0. Okay, and the final case, if the degree of the numerator is greater than the degree of the denominator. So again, looking up here, if the degree of the numerator is greater than the degree of the denominator, then this is going to simplify to, x to the n minus m. So something in the numerator over 1. And as x goes to positive infinity, that's going to shoot off to positive infinity. Okay, so that's why we're going to have infinity right here. And if it shoots off to infinity, that means there's not going to be any horizontal asymptote. Okay, so that's where case 3 comes from. If the degree of the numerator is more than the degree of the denominator, then there is no horizontal asymptote. Okay, so that was kind of a lot. What's important for you to be comfortable with is just like, how do we apply this knowledge to learn about horizontal asymptotes? So we're going to look into that in example 5. We want to find the horizontal asymptote of each. So for this first one, we've got this quadratic function x squared plus 3x plus 1 over another quadratic function, 2x squared plus x. So in this case, the degree of the numerator, p, is equal to 2, and the degree of the denominator q is also equal to 2. So these are equal degrees. So I'll say since degree of p is equal to the degree of q, we have a horizontal asymptote and it's going to be the line y equals a sub n over b sub m. So that's like, the ratio of the leading coefficients. So in this case, leading coefficient in the numerator is 1, right? That comes from right here. And the leading coefficient of the denominator is 2. So y equals 1/2 is our horizontal asymptote. Cool. So there it is. So if we were to look at the graph of this function here, we're not going to do the whole graph here, but at x equals 1/2, or sorry, at y equals 1/2, we're going to have a horizontal asymptote that goes like that. And if you factored the denominator, and solved for 0, you would see that we have a couple of different vertical asymptotes at x equals 0, and I believe at x equals -1/2. So I think the graph for this one ends up looking something like this. But anyway, the important feature that we're thinking about right now is just this horizontal line, y equals 1/2, which this graph is going to approach on the left and on the right. So there it is. Equal degree means that we have a horizontal asymptote ratio of the leading coefficients. So for this next one, looking at this function here, the numerator is cubic, the denominator is quartic, so 4th degree. So the degree of p in this case is 3. The degree of q is 4. So the degree of the numerator is less than the degree of the denominator. So that means that the horizontal asymptote is going to be, by this rule, y equals 0. Okay, so as x values go far out to the right and far out to the left, we're going to see the output values of the function just approaching the x-axis, kind of like those first couple examples we saw, or that first example we saw. And this last one, we can see that the degree of the numerator is going to be 4, and that's going to be greater than the degree of the denominator, which is going to be, degree 1. So 4 is greater than 1. So that means that there is no horizontal asymptote. Okay. And, if we took this, and, now that we have polynomial long division, if we divided this, like using long or synthetic division, we would end up with something that looks kind of like a polynomial. Like we would end up with some function that looks something like 4x cubed plus blah, 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 and then, plus the remainder over the divisor. But really, it would look like a polynomial. So it kind of makes sense that we wouldn't have a horizontal asymptote for this one. We're going to end up having end behavior that goes, like this. It's a degree 3 polynomial, essentially. So anyway, no horizontal asymptote for that last one. Okay, and then we've got one more type of asymptote to talk about here, and eventually we're going to get around to actually graphing some of these and, engaging with these functions in a more kind of holistic way. So let's talk about slant asymptotes so that we can do that. So assume p of x and q of x have no common factors if the degree of the numerator is exactly 1 higher than the degree of the denominator. Okay, so in other words, p, the degree of p is equal to the degree of q plus 1. Okay, so the degree of p is just 1 more than q. Then the graph will have a slant asymptote in the form y equals mx plus b, and we can use long division to find that slant asymptote. So I kind of, was hinting at that, talking about long division up here. It turns out long division is going to play an important role in this section. So let's find the slant asymptote of this thing. So first of all, the degree of q, or my bad, the degree of p is equal to 2, and the degree of q, this is linear, so it's equal to 1. So seeing that, 2 is just 1 more than 1, that sort of confirms that I'm going to have a slant asymptote. All right, so now what we're going to do is we're going to find the slant asymptote, and the way we do that is using long division. Okay, so another way to express f of x is going to come out of this. So I'm going to divide. I'm going to divide x squared minus x minus 6 over x minus 5. And I can do this using long division. I could also use synthetic division, but I'm just going to do long division this time. So the way I do this, think back to section 3.2 where we talk about this. Is that the right section? 3.2? Yeah, I think so. So how many times does x go into x squared? Well, it goes in x times. So I'm going to write the x up there. Multiply through the divisor and I get x squared minus 5x. And then I want to subtract those, so I distribute through a negative. And I get positive 4x, and then I bring down this minus 6. Now, how many times does x go into 4x? Well, it just goes in 4 times. So I'll write plus 4. I'll multiply through that plus 4 and I get 4x minus 20. And then I'll distribute through a negative. And I'm going to end up with positive 16. And since x doesn't go into positive 16, that is my remainder. So that is r of x. Okay, so now what I can do is I can rewrite f of x as quotient, so x plus 4, plus the remainder, which is 16, over the divisor, which is x minus 5. So now notice that, so I'll say now, we can see that as x goes off to positive infinity, f of x, which is equal to x plus 4 plus 16 over x minus 5. Well, this factor right here, or sorry, this term right here, notice that as x goes off to positive infinity, if I put in like, I don't know, 10,000 or something, if I put in 10,000, this is going to be 16 over 9,995, right? Or if I put in a million, I'm going to have 999,000, something like that. So basically we can see that this whole thing here is going to 0. So basically what f of x is doing as x goes to positive infinity is it's kind of approaching this line, y equals x plus 4. You know, it's like the remainder term kind of goes away. It gets so small that we don't even really pay any attention to it. So basically it goes off to positive infinity. But it's going to follow this line right there. So this line ends up being the slant asymptote. So the slant asymptote is just equal to this line, y equals x plus 4. And your rule, just to remember, like how to get this y equals x plus 4, this is basically just the quotient from the division problem, p of x divided by q of x. Okay, so that's how we're going to deal with this. If you ever see a rational function where the degree of the numerator is just one more than the degree of the denominator, like we saw in this case, you're going to do the long division, and basically whatever you end up with in the top, you know, whatever your quotient is, you know, set y equal to that expression, and that's going to be your slant asymptote. Cool. So let's keep going. We've got, you know, now we have a few problems that we can do, and we can just enjoy how interesting these functions are. We kind of got all the definitions and all the stuff we have to memorize out of the way. Let's look at some actual problems. So number 7, we want to find a rational function that satisfies a few different things. We want to have a vertical asymptote at x equals 1. We want a horizontal asymptote at y equals 2, and we want a y-intercept 0, 1. Okay, so I know you guys hate these problems. Or you don't hate them, but you love them actually. You secretly love them, but they challenge you. Okay. So the recommendations that I've made in the past are like, if you're given a problem like this where it says find the function, you know, your answer is going to be the function, right? You're going to have some rational function as your answer. We have to figure out what it is. And you're given a bunch of different requirements, and my recommendation is always like, you know, take it slow, just think about one thing at a time. So let's do that. So vertical asymptote at x equals 1. So what this means is that x equals 1 is a 0 of the denominator. Okay, so that means that x minus 1 is a factor of the denominator, right? Remember, there's this, you know, there's this connection between the zeros and the factors. Okay, so that's helpful, you know, as I'm kind of like building up my answer down here. I know one thing already. I know that I'm going to have a factor of x minus 1 in the denominator. Cool, so we're on our way. So now we have that the horizontal, so looking at this next thing, horizontal asymptote is y equals 2. Okay, so since y is equal to 2, so think back to our cases, right? If the degree of the numerator and denominator are equal, you know, that's when we get a horizontal asymptote, which is not infinity and not 0. So the horizontal asymptote is, I'm going to think of it as 2 over 1. So there are a couple implications here. So this means, so I'll say, so that means that the degree of p is equal to the degree of q, right? And the other thing that this tells me is that, so I'll say and, that means that a sub n over b sub m, or I can actually say b sub n since they're going to be the same degree. So the ratio of the leading coefficients is going to be 2 over 1. All right. So I'm going to sort of think about this as like, you know, there's going to be a factor of 2 up here in the numerator. Okay, and the other thing that I have to be sure of is that the degree of this numerator is going to be the same as the denominator. So, I'm going to try to keep this as, a degree of 1. So I'll just write this as x. And okay, I don't know what this factor is though. Notice that they don't tell us like what the zeros of this function are. So for now, I'm just going to say x minus a in the numerator, because I still have one more requirement to satisfy. So the last requirement is that it has a y-intercept of 0, 1. Okay, so what this means is that if I plug in 0, so basically f of 0, I should get an output of 1. Okay, so now what I have so far right here, I'm going to sort of like substitute into this equation here. So 2 times x minus a over x minus 1. Oh, sorry, I should substitute in 0 for x. So really this should be 0 minus a over 0 minus 1. This should be equal to 1. Okay, and now I'm just going to basically solve for the a value that makes this a true statement. Okay, so this simplifies to 2 times negative a, whoops, not 8a, over negative 1 is equal to 1. So, I can simplify here. So negative 2a is equal to, so I'm going to multiply both sides by negative 1. And then divide by negative 2, and I get a is equal to 1/2. Okay, cool. So now I'm just going to sort of update this. So a in my function, I'm going to replace it with 1/2. And now just to simplify, just to clean it up a little bit, I'm just going to distribute that 2 in there, and here's what my final answer is going to be. F of x is equal to 2x minus 1 over x minus 1. And I'm going to put a box around that. Okay, so I just kind of broke that problem down, one piece at a time and kind of pieced this thing together. And now that I have my answer, something I usually do, and if you're working on a test and you have time, this is a good idea, is just kind of check each one of these and make sure. So I mean, okay, do I have a vertical asymptote at x equals 1? Well, it's a 0 of the denominator, and it doesn't cancel with any common factor in the numerator, so yes. Is the horizontal asymptote y equals 2? Well, the degree of the numerator and denominator are both 1, so they have the same degree. So then the horizontal asymptote is going to be the ratio of the leading coefficients, which is 2 over 1, which is 2. So, check, it satisfies that, that second condition. And then the final one, is f of 0 equal to 1? Well, if I plug in 0 into this thing, I get, 0 minus 1 over 0 minus 1, which equals negative 1 over negative 1, which equals 1. So check, it works. So it doesn't hurt to go through and just kind of check each of these properties. Doesn't take long, and it could save you a lot of points on the exam. Okay, so for example number 8, we want to find the intercepts and asymptotes of the graph of this rational function f of x. And I've got quadratics in the numerator and denominator. So x squared minus 5x in the numerator and x squared minus 4 in the denominator. Okay, so I guess we can start with intercepts. So for the intercepts, really we're just looking for the x and y intercepts. So we've already discussed this in the past. So y-intercept, remember there's only going to be one y-intercept. And that's because this is a function, right? And the y-axis is a vertical line. So we can only, by the vertical line test, we can only have one intersection point with that line. So the y-intercept is going to be this ordered pair 0, f of 0. And plugging in 0 into our function, we're going to get 0 over negative 4 as our output. So our y-intercept is at the origin, 0, 0. So that's one of our intercepts. And now to find the x-intercepts, you might remember the way that we do this is we set f of x equal to 0 and solve for x. So, what this would look like is we would get x squared minus 5x over x squared minus 4 equals 0. Okay, so there's a little trick here that makes life a lot easier. I mean, one way to think about it is, hey, if we just multiply both sides of the equation by x squared minus 4, that denominator there, we're just going to be left with the numerator on the left side, and we're still just going to have 0 on the right side, because 0 times x squared minus 4 is just 0. But another way to think about it is, really, in order to get the x-intercepts or get the the zeros of this function, really we just need the numerator to be equal to 0, because that's the way that fractions work, right? Like if we have a fraction and it's equal to 0 over some denominator, it doesn't really matter what the denominator is. This is going to be equal to 0. Okay, so a trick is, if we're trying to find the x-intercepts of a rational function, just set the numerator equal to 0. So I'll just say trick, just set the numerator equal to 0. So I can get away with just, x squared minus 5x, set that equal to 0 and solve. And I'll solve by factoring. I can pull out that common factor of x, and I get these two zeros, x equals 0 and x equals positive 5. And, as we've seen before, this gives us x-intercepts 0, 0, and 5, 0. Cool. So there we have all of our intercepts. So now let's talk about asymptotes. Okay, so if we want to find, I guess let's start with vertical asymptotes. So the vertical asymptotes, I get these by setting the denominator equal to 0 and solving. Okay, so what that's going to look like is x squared minus 4 equals 0. Okay, so to find the x-intercepts, we set the numerator equal to 0. That gives us the zeros of the function. To find the vertical asymptotes, set the denominator equal to 0, and that will give us the values of x that make the function undefined, because they would make the denominator 0. So I could solve by factoring. This factors to x plus 2 times x minus 2. So I get these two solutions, x equals negative 2, x equals positive 2. And these are just equations to these two vertical lines, which are the asymptotes. Okay, we're moving right along here. Next, I want to find the horizontal asymptote. So remember, there's only going to be, there's going to be at most one horizontal asymptote. Okay. And the way we've been talking about this is like, we've got this function f of x, which is equal to x squared minus 5x over x squared minus 4. So notice that the degree of the numerator is equal to 2, and the degree of the denominator is also equal to 2. Okay, so since the degree of the numerator and denominator are equal, then the horizontal asymptote, is just the ratio of the leading coefficients. Right, so the way we wrote this before is y equals a sub n over b sub m. So in this case, it's, y equals 1 over 1. So it's just the line y equals 1. All right. Cool. So from here, really we have all the super important information. The intercepts and the asymptotes, those are the most, kind of telling pieces of information. So what I'm going to do is I'm going to plot my axes, and I'm going to draw in these asymptotes, and I'll plot my intercepts. And then I'm going to come in and do a table of values and just get a couple extra points and, make sure that my graph looks okay. All right. So I will just kind of, put my axes in pretty central locations. So there's my x-axis. There's my y-axis. And I will plot, okay, let's start with the asymptote. So I have vertical asymptotes at x equals positive 2, little dotted line there, x equals negative 2. And then I have a horizontal asymptote at y equals 1. Okay, cool. And now I want to plot my intercept. So my y-intercept is right there at the origin. That's also one of my x-intercepts. And then I have another x-intercept at 5, 0, so over here. Okay, so, my guess is that my graph is going to look something like, that on the ends. And then something's going to be going on in here. I'm not so sure yet. So notice that we really do need to, use a table of values in this case. So, I wrote a little too big, so I'm going to do my table of values right over here. So x, those will be my inputs, and then f of x will be my outputs. And I'm going to use my I'm going to use my calculator for this because I'm going to be getting some pretty big numbers, it turns out. So that tends to happen when we are working with functions that have asymptotes. Because of course, you know, close to asymptotes, what happens, vertical asymptotes, I mean, is we see the x values getting really, really large or really, really small. So I definitely prefer to have my graphing calculator on hand to do this. Okay, so I guess let's start with this kind of like, you know, left branch of our graph. So I'll look at some values like, how about -5, -4, -3, and I can't put in -2 because that's where my asymptote is, but maybe like -2.1. Okay, so I picked -2.1 because that's like just right here, just to the left of that asymptote. And you know, this is a technique we'll use. It's like you pick an x value which is really close to one side of the asymptote and basically see, are we getting a really large output or a really small output? And that will indicate which direction the curve is going close to that asymptote. So okay, let's do this. So I put in -5 in my calculator and I'm getting about 2.4. I put in -4 and I get out 3. I put in -3 and I get 4.8. And I put in -2.1. So okay, really big number, really small number. Let's see. And I get 36.4. Okay, so from that, you know, that gives me a couple ordered pairs here. So there's, or let's see, -5, 2.4, -5, 2.4, so around there. -4, 3, -3, 4.8. So, okay, yeah, it's definitely looking like my curve will have that kind of behavior in that region. Okay, great. So that is, you know, that first little portion of the graph. Here, maybe I'll switch colors because now I'm looking in this middle region here. So again, same kind of question. It's like, close to these asymptotes, what is the behavior going to be? Is it going to be going down towards -infinity right there, or is it going to be going up towards -infinity? So the way that we check is we just plug in a value that's really close to that asymptote, but just to the right. So, you know, what's a good value that's just to the right of that asymptote at x equals -2? Well, a number that's a little bit bigger than x equals -2 is like -1.9. So that's a value I'll plug in. And then I'll check, you know, -1 and +1, and how about +1.9? Okay, so I hope you're seeing kind of the strategy. It's like, it's kind of a unique approach to the table of values. Like when we have asymptotes, we want to pick values that are really, really close so that we can tell what the behavior is there. So anyway, using my calculator, I'll plug in -1.9, and I get -33.6. Okay, plug in -1 and I get -2. Plug in +1 and I get 1.3. Plug in +1.9 and I get 15.1. All right, so got a few ordered pairs here. There's 1, 1.3. So the graph in the middle is going to look like this. Cool, so there's that middle branch. And now on the right part, how about I'll use red ink for this last little region. So I'm going to plug in a value of x that's really close to that asymptote at x equals 2, but just on the right. So how about 2.1? And then maybe I'll plug in 3 and 4. I think that'll probably be enough. So I plug in 2.1 and I get out negative 14.9. I plug in 3 and I get negative 1.2, and then I plug in 4 and I get negative 0.3. So it looks like our graph is going to do something like this. Okay. Well, so this is obviously a really cool looking graph. These are really, really interesting functions once you plot them in the coordinate plane. There's a lot of diversity, in just within rational functions, what they can look like. These are some of my favorites. I love these where you have like, multiple vertical asymptotes and a horizontal asymptote, and you're just shooting off to infinity in all these different directions. It's pretty crazy looking. But that's the process for getting those graphs. Always start with the big things first, right? So intercepts and asymptotes. And then you use those guidelines to sort of, make some informed decisions about what values you're going to plug into your table of values, with extra attention to, the vertical asymptotes, and plugging in numbers like, really close to the left and to the right of each vertical asymptote, so you can tell whether they're going up to positive infinity or negative infinity, and all that stuff. Cool. I hope that went all right for everybody. We're going to do another one. So example 9. So we want to do the same thing, find the intercepts, asymptotes, and graph this thing. So this is kind of scary looking because we've got a cubic function in the numerator, a quadratic function in the denominator. Okay. Well, let's get to it. So we'll start with the intercepts. I'm going to try to write a little smaller here. I've gotten in the habit of writing too big. So the intercepts. So let's start with the y-intercept. So I will plug in 0. So 0 and then f of 0 is the y-coordinate. So 0, and then I think I'm going to get 0 over 1. So again, I'm going to have a y-intercept at the origin. That's going to be one of my x-intercepts as well. So for my x-intercepts, I want to, just like the last problem, set the numerator equal to 0 and solve. So that's going to look like this: 2x cubed minus 6x squared minus 8x equals 0. And okay, so we want to solve by factoring. This is a cubic function. So you might be thinking, oh no, I have to use the rational zeros theorem and synthetic division to guess the first 0. Actually, we don't, because we have a common factor of x here. So I'll pull out that factor of x. You know what? Why not pull out the 2 as well? So I'll pull out 2x, and then I'm left with x squared minus 3x minus 4, if I did that correctly. Does that look all right? Yeah. And this quadratic here, I believe, so here I can do one of these things and say, okay, what two numbers multiply to negative 4 add to negative 3? Maybe negative 4 and 1. So that means that this factors to x minus 4 times x plus 1 equals 0. And check it out. If any of these factors equals 0, the whole thing equals 0. So that gives me solutions x equals 0, x equals 4, and x equals negative 1. So that gives me x-intercepts at the origin. I kind of knew that one was coming. 4, 0, and negative 1, 0. So, okay, let me box all of my intercepts up here. Good. So now let's talk about asymptotes. So we'll look at vertical asymptotes first. And these are just the zeros of the denominator, right? So I'll set the denominator equal to 0. And, okay, x squared plus 1 equals 0. And, oh, this is kind of interesting. Notice that there are no real solutions to this, right? Like I could solve this by taking square roots if I wanted. And I would get x equals plus or minus root negative 1. In other words, you know, that's plus or minus I. So I, the imaginary number, it's not on the x-axis, so we're not going to have any, you know, like, how do we graph this line, x equals I? It doesn't exist in the real xy plane. So what this tells us is that there are no vertical asymptotes. Okay, you know, no big deal. We'll find a way to work around that. Let's talk about horizontal asymptotes now. So looking up at our functions, so remember, we have these cases. Let me go back. Where did we talk about this? We have these cases for horizontal asymptotes, and the way that we tell is looking at the degree of the numerator and the degree of the denominator, and depending on how those match up, that will, you know, tell us what type of asymptotes we have. So remember, we have for the problem we're working on now, it's cubic in the numerator, and then quadratic in the denominator. So it's like the degree of the numerator is equal to 3, and the degree of the denominator is equal to 2. So basically, you know, we're in this case right here, where the degree of p of x, the numerator, is greater than the degree of the denominator. So there is going to be no horizontal asymptote. Okay, but there's a different type of asymptote that you might remember. Notice that the degree of the numerator is just 2 plus 1, right? It's 1 more than the degree of the denominator, and this puts us in the special case where we have slant asymptote. So we're going to use long division. Remember, we do the long division. Here's this last example. And whatever the quotient is from that division problem is going to be the equation for our slant asymptote. Okay, so, all right, back down here. So the degree of the numerator, p, is equal to the degree of the denominator, q, plus 1. Okay, so what that means is there is no horizontal asymptote. But there is a slant asymptote. So we're going to do a little polynomial long division here. So I think I've got a nice little space right here to do it. So we want to divide, so x squared plus 0x plus 1. Remember, we have to do that. So that's our divisor, and then our dividend is 2x cubed minus 6x squared minus 8x. Just check and make sure I did that right. Yeah. So let's do it. And remember, I can't use synthetic division here because my divisor is not linear. So, oh well. Okay, so how many times does x squared go into 2x cubed? Well, I think that it would be 2x times. So 2x. Oh, and I should put a plus 0 on the end here because there's no constant term. Remember, we like to keep everything lined up. Okay, so multiply 2x through my divisor and I get 2x cubed plus 0x squared plus 2x. And then I want to do this subtraction problem, so I'm going to distribute through a negative. And I'm left with negative 6x squared, what is that, minus 10x. And then, bring down the plus 0. So how many times does x squared go into negative 6x squared? Well, negative 6 times. So we put in, multiply negative 6 through our divisor. So negative 6x squared plus 0x minus 6. Distribute through a negative, and I think I'm going to get a remainder of negative 10x plus 6. So there's my remainder. But remember, I actually don't really care about the remainder too much because my slant asymptote is just going to be defined by this right here. Okay, so check it out. That is going to give me my slant asymptote. And it's just going to be y equals 2x minus 6. And I will put a box around that. All right. So now from here, this is an interesting case, right? It's like we don't have vertical asymptotes. We don't have horizontal asymptotes. We've just got a few x-intercepts and a slant asymptote. So let's see what's up with this. All right, so I'll start by drawing in my axes like before. And I'm going to keep everything pretty central here. Just meaning the origin is going to be in the middle of my grid. And I'll mark out my intercepts. So I have those at 0, 0, -1, and +4. And the only other thing I have is my slant asymptote, which has, okay, so it has y-intercept -6, so down there, and then it's got slope +2. So I'm going to draw in this dotted line. looks something like that. So there's my slant asymptote. So I'm going to do a table of values now, and okay, so what areas do I need to know about? Because I honestly don't have any idea what the behavior is going to be like for this curve here. So I'll start a little table of values over here. And okay, so I want to know what's happening to the left of that far left 0. So I'll plug in like -2, -3, -4. Maybe that's enough for now. I'll plug in -0.5 to see what's happening between those two zeros. Between the 0 at -1 and at 0. And then I'll plug in 1, 2, 3, and then on the right side of that last 0, maybe I'll plug in 5 and see what happens. So let's do this. I'll go to my calculator, and by the way, the way that I do this is I use the trace feature. On my graphing calculator. That's how I'm able to do all this really quickly. So we talked about this in a previous lecture. I showed you my calculator that I use. So this is a graphing calculator thing. If you have a calculator other than the TI-83 that I use, there are plenty of videos on YouTube. You can look up, just trace feature of graphing calculator, and you'll find a million tutorials. But that's how I'm doing this real quickly. So I'll plug in each of these numbers. So -2, I get out -4.8. Put in -3, I get out -8.4. Put in -4, I get -11.3. And then -0.5, I get out 1.8. Put in 1, I get -6. 2, -4.8. 3, -2.4. And 5, I get 2.3. So I'm going to plot each of these now and see what I end up with. So, okay, 0.5, 1.8. Just kind of working through each of these. One, I get -6. All right, and I think I'm starting to see what this graph is going to look like. So remember, the curve is going to kind of tend towards this slant asymptote here. So what it looks like is, maybe starting at the origin and going to the left, the curve is going to go up, it's going to go through that ordered pair, it's going to come back down, and then it's going to go through these points, and it is going to sort of get close to that slant asymptote. It's never going to touch the slant asymptote, but it's going to kind of, get closer and closer to it as x goes to -infinity. And then what's interesting is on this side, the curve is going to go down, and it's going to go through that point there, and then it's going to sort of curve around. And then on the right, it's going to sort of approach that slant asymptote from below. So we are going to end up with a graph that looks like this. Okay, so because there are no zeros to the denominator, remember the denominator didn't have any real zeros. The domain for this function is technically all real numbers, so we don't have any gaps. We don't have any, vertical asymptotes or anything. This is actually a continuous function for all real numbers. Really, all that it has going on is it just kind of converges to this line y equals 2x minus 6 with a weird little squiggle in the middle. So that is it. That's our function f of x. Okay, great. So example 10, and oh my gosh, this is the last problem in chapter 3. Amazing. So same thing, we want to find the intercepts and asymptotes, and we want to graph this function, f of x equals x plus 2 over x cubed plus 8. Okay, well, we'll kind of go through the same process that we have been. So I'll find the intercepts. So y-intercept is going to be this ordered pair 0, f of 0, which in this case is going to be 0, and then I think I get just 2 over 8. So that's the ordered pair 0, 1/4. So there's my one y-intercept. For my x-intercepts, I'm going to set the numerator equal to 0. So x plus 2 set equal to 0. So I'm just going to have this one x-intercept at x equals -2. So, the ordered pair would be -2, 0. Okay, cool. So now I want to talk about intercepts. Or sorry, not intercepts. Asymptotes is where we're headed here. And so asymptotes. So our function here is equal to x plus 2 over x cubed plus 8. Okay, so I kind of want to start by factoring that denominator. So this is the sum of two cubes, and there's actually a formula for this. This factors to like a linear factor times a quadratic factor. So there is a formula here, but I don't memorize that one. So to factor the denominator, I'm going to basically use synthetic division to try and guess a 0. So let's factor the denominator real quick. So I'll just do this over here. So factor q of x, which is equal to x cubed plus 8. So remember the possible rational zeros. Are going to be, in the form p over s, where p is, all the integer factors of 8, so plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, all over plus or minus 1, where, s, that's the integer factors of the leading coefficient, 1. So, I might guess some number, like maybe I'll guess, let's say, is x plus 2 a factor? So what I would do there is I would look at, c is equal to -2, and then I'd do a little synthetic division. And for the coefficients of my dividend here, I'd put 1, 0, 0, and 8, right? So the zeros, that's for the x squared coefficient and the x coefficient. So here, let's do it. I'll bring down the 1, multiply by -2, add down, multiply up, I get +4, add down, multiply up, I get -8, I get 0. So this gives me, so remember the 0 at the end means that it divided evenly because that's our remainder. So that means that -2 is a 0, thus x plus 2 is a factor. And the remaining factor would be x squared minus 2x plus 4, where those coefficients came from right there. So anyway, some people just have the sum of two cubes formula memorized. I don't. I always end up doing this. But so this factors to x plus 2 times x squared minus 2x plus 4. And this creates a pretty interesting little scenario because, look, we have a common factor in the numerator and denominator, which is x plus 2. Okay? Okay, think back. What does this mean again? How does this get reflected in the graph if we have a common factor in the numerator and denominator of a rational function? This means that we have not a vertical asymptote at x equals -2, which is normally what we think when we see that's, a factor of the denominator. It means we have a hole in the graph. Okay, so here's what we learned. So I'll say, f has a hole in its graph at x equals -2. But other than that, so otherwise, f has the same graph as y equals, remember basically just what the function is with that factor canceled out. Y equals 1 over x squared minus 2x plus 4. Okay, so this is tricky, but it's something we have to watch out for. So now it's like I'm aware that I'm going to have a hole in the graph at x equals -2, but now, when I'm thinking about like, all right, what are my asymptotes and all that stuff, I'm really going to be thinking about this function. Okay, so I've got a hole here. Maybe I'll put a box around this. So we've got a hole in the graph at x equals -2. But otherwise, it's going to look like this function here. So now let's think about, do we have any vertical asymptotes? So for this, I'm going to set the denominator equal to 0. But at this point, I'm just setting this sort of like simplified denominator, x squared minus 2x plus 4. Right, because any remaining zeros here, those are going to give us vertical asymptotes because they don't have a factor in the numerator to cancel with. So this thing does not simplify, or sorry, it doesn't factor very nicely. So I'm going to use the quadratic formula. So x equals -b plus or minus square root b squared minus 4ac. So that's going to be minus 4 times 4 times 1, so it's going to be -16. all over 2a. And right away, I see that I'm going to get a negative number inside of this square root, which means that I'm going to just get complex solutions. So, this right here is going to end up being the square root of, what is it, negative 12? So there are going to be no real solutions to this. No real solutions. So that means no vertical asymptotes. Okay, so this is a very interesting example because, our denominator in this case was cubic. So it's like, it's you would expect to have at least one real zero of the denominator that would cause a vertical asymptote. But what ends up happening is, x cubed plus 8x, this has one real zero and two complex zeros. And the one real zero canceled with the numerator, so that wasn't an asymptote. It just gives us a hole in the graph. So no vertical asymptotes. Oh well. And then for horizontal asymptotes, we can do this quickly. Since the denominator has higher degree than the numerator, this is, let me just scroll up real quick. So the degree of p is less than the degree of q. So we are looking at this situation. So that means that our horizontal asymptote is y equals 0. So, okay, just quickly, degree of p is less than the degree of q. So the horizontal asymptote is going to be the line y equals 0. Okay, let's get a graph going here. And as always, we can jump in with whatever, we can make a table of values and fill in any gaps. So, all right, let's see, where do we want to start? I've got a y-intercept at 0, 1/4. So here, maybe I should, here, let me get my calculator fired up here because I'm going to have to do a table of values here. Okay, so here's what I'm going to do. Notice that my y-intercept is pretty small, right? 1/4. So I'm going to set my scale a little differently than I did in previous problems. So along the x-axis, I'm just going to count by ones, so that will be 1, 2, 3, 4, and so on. So normal scale along the x-axis. But along my y-axis, my output values are going to be pretty small. So what I'll do here is I will have so I will just set my scale so that each of these tick marks is a quarter. Okay, so that means that this right here is going to be 1. And that's going to be 1/4, 1/2, 3/4, 1 1/4, 1 1/2, and so on. Okay, so then I can put my y-intercept right there. And then let's see, what else do I have going on? I have an x-intercept at -2. So that'll be right there. And I have a horizontal asymptote at y equals 0. So I'll put that in there. And I have a hole in my graph at the x-intercept. Okay, so that little, x-intercept, that blue point that I put in there, I'm going to draw that as an open bubble actually. So open bubble right there. Okay, great. So now from here, I'm going to make a table of values just to get a few extra points. All right, so I'll plug in, like -3, -4. I'll plug in -1 between, my x and y axis there, or my x-intercept and my y-axis. I already have 0. I'll plug in 1 and 2 and 3, and I think that's probably enough. So note that I can, for my f of x, since I'm plugging in numbers other than 0, it turns out that it doesn't matter if I plug it into the original function, the x plus 2 over x cubed plus 8. It doesn't matter if I plug it into that or 1 over x squared minus 2x plus 4. These two values, or these two expressions, are going to return the exact same outputs except for at x equals -2. Right? Because the only difference between these two expressions is, we cancel out a factor of x plus 2 in the numerator and denominator to get from, this first one to the second one. So it doesn't matter which of those you plug into. So here I'm gonna do it. So I will plug in -3. I'm doing this all using my calculator. Put in -3 and I get out 0.05 approximately. Put in -4 and I get 0.03, or let's say 0.4 if I round it up. And I can plug in -1 and I get 0.14. Plug in 1 and I get 0.3. Plug in 2, I get 0.25. I plug in 3 and I get 0.14. Okay, cool. So I'm just going to plot each of these points here. So what I have happening is I get these points, looking off to the right of the y-axis. So 1.3, that's like 1 and a comma 1/3. So like around here. And then it goes back down, and then our values start approaching the x-axis because we have an asymptote there. So it's going to go down like that, and then on the left side it's going to be the same kind of thing, and then we're just going to get really close to the x-axis on the left side as well. Okay, so that is it for chapter 3. So yeah, these problems with graphing rational functions can be pretty involved, but they're not really too hard. There's so many guardrails, just using the intercepts and the asymptotes, it's really, those features communicate so much information about the graph. So by the time you get to, doing the table of values, it's not too difficult. So yeah, have fun with these problems, and I will see you in the next chapter. Chapter 4, we're going to start talking about angles and trig functions and all that cool stuff. So I will see you there.